네, 안녕하십니까.
Good afternoon, ladies and gentlemen. I'm Pang Min-sun, Energy Officer at the Danish Embassy in Korea. I'll be hosting the seminar today. This seminar is based on the feedback from diverse stakeholders and is planned to provide an occasion to think about why we need to be thoroughly prepared for power grid and how we can prepare in order to expand renewable energy to achieve 2050 carbon neutrality goal. To this end, we would like to talk about the case studies of Denmark, which started energy conversion earlier than Korea and successfully built a wind-centered power system. This seminar is co-hosted by Danish Embassy in Korea, the Danish Energy Agency, and Energy Conversion Forum, and joined by Energinet. In mid-August 2019, a largest blackout took place in UK. It was the largest in 10 years. The 400 kilovolt class power transmission line was the cause of the blackout. A lightning strike hit the line, and after that, large-scale offshore wind power plants and gas-fired plants each went offline. At the time, the power transmission operator National Grid ESO had a backup facility of 1,000 megawatt, but because of the cumulative supply caused by the lightning strike was 2,100 megawatt, frequency fell below the safe limit and the part of the grid was cut off. Witnessing the UK power outage, experts around the world realized the importance of having sufficient reserve power, upgrading power grid operation, and we were able to take note of the instability of the power plants, especially when power supply is concentrated in one place. The power outage is not only a problem for the UK, but it is also a problem that can occur in other places, and Korea is no exception. And internal factors such as changing power and demand dynamics such as renewable energy expansion, inexperienced operation, and external factors such as natural disaster can be the cause of such problems. Korea, as it strives to achieve a balanced energy mix, we need to properly understand the different technical characteristics of each power resources and develop new technologies for stable power grid. Governments, companies, research institutes such as the Ministry of Trade, Industry and Energy, KEPCO, are concentrating their efforts on this. Today's seminar was held by Danish Energy Agency, an affiliate of the Danish Ministry of Energy, Climate, Utilities, Energinet, a Danish power transmission operator, and KEPCO, Electric Power Research Institute. So through today's discussion and Q&A, we'll discuss how to practically build a new power system for the expansion of new and renewable energy. So before we start today's seminar, we would like to invite His Excellency EInar Jensen, Ambassador of Denmark to Korea, for congratulatory remarks. He was supposed to join us offline, but because of another engagement, he has given us a video recording of his welcome remarks. Please welcome him with a big applause.
Distinguished guests, dear colleagues, ladies and gentlemen. My name is EInar Jensen, and I'm the Danish Ambassador in Korea. It is indeed a great pleasure for me to open up this workshop as we further strengthen our partnership in advancing the integration of renewable energy in the Korean grid system. A special thanks to Professor Young-Hwa Chung and Energy Transition Forum for arranging this workshop in cooperation with the Danish Embassy in Korea and the Danish Energy Agency. Since 2011, Denmark and Korea have been collaborating on the green agenda under the Green Growth Alliance. Through these years, our two nations have come to learn much from each other and have continuously strengthened our united goals to secure a sustainable source of energy for the future. Our consistent collaboration have resulted in ambitious goals, and I'm pleased to see Korea is aiming to reduce the carbon emission by 40% in 2030 and go carbon neutral in 2050. The strategic alliance between our two nations is created in order to help each other make these goals come true. Being the Danish ambassador here in Korea for nearly 3 years, I have witnessed the broadening will of the Korean people to obtain a more sustainable source of energy. Korea's industrial capabilities are extremely impressive, and simultaneously, the Korean market actively pushes for green transition and aims to place Korea in the very top of the world. Korea is aiming to produce 12 gigawatts of renewable energy in 2030, but in order to utilize this energy, there is a huge challenge for the modernization of the grid system, and this will need an equally ambitious plan. The will is indeed there, despite the current and impending challenges. I am great confidence that this commitment will keep us on track to achieve these ambitious goals. As part of our growing strategic alliance in pursuing renewable energy, I am honored to be able to welcome the Danish Energy Agency in Korea. They will have the opportunity to elaborate further on the many lessons learned from Denmark and present tangible solutions to the current issues in Korea. Together with their colleagues from the Danish TSO, Energinet, I'm assured that they will make us all more knowledgeable about these issues today. And I hope that Korea can learn from the Danish experience with a focus on the integration of renewable energy into the grid system. With such a showing of strong will to overcome the current issues concerning the grid connectivity and curtailment, I'm optimistic that Korea will be able to show the world the solutions in actions on the unprecedented scale. I wish you all the most fruitful day with interesting discussions and exchange of knowledge so that we can together envision the sustainable energy future. 감사합니다.
네. Thank you very much, Ambassador. Now, before we play the welcome remarks video, if you need interpretation services, please use the receiver on your table for simultaneous interpretation services. Now we would like to hear the welcoming remarks by Deputy Director General of Denmark Energy Agency, and he has also joined us through a video recorded speech.
Good afternoon. My name is Stig Pedersen, and I'm Deputy Director General at the Danish Energy Agency. Unfortunately, I'm not able to participate today, but I'm pleased that technology allows me to do this intervention. For many years, Denmark has pioneered the transition to renewable energy. In 1999, we built the first offshore wind park ever. Around year 2000, we had an average of 12% of variable renewable energy in our mix. And today, more than 50% of our electricity is generated by wind and solar power. One of the driving reasons for this transformation has been the liberalization of the power sector. The liberalization has resulted in a much more efficient use of resources, with better interconnected geographical areas and flexible thermal power plants that can respond to variations in the production from wind and solar. The current government has set a target of climate neutrality in 2050. Denmark has furthermore introduced a 70% greenhouse gas reduction target in 2030 compared to 1990 as a stepping stone towards the target of climate neutrality. While having a large percentage of variable renewable energy in the power mix, Denmark also holds top rank when it comes to security of supply, with only 20 minutes of lost load per year on average. With the ambition of maintaining a high level of security of supply, 100% of our electricity will be from renewable energy in 2030. This will be particularly driven by an expansion of offshore wind. Offshore wind has the potential to play a central role in the green transition. The harvest of this potential depends on government strategies as well as industry contributions including needs to manage maritime spatial planning and, of course, grid development. In 2020, the Danish government decided to develop and build 2 energy islands, and these will serve as power plants gathering and collecting green electricity from surrounding offshore wind farms. These islands will ensure distribution of power between countries connected via the electricity grid, both to Denmark and to neighboring countries. The long-term vision goes beyond the national borders, and the energy islands are preparing us to enter a new era of green energy production. This is a paradigm shift in the way we approach offshore wind with interconnectors to bordering countries, and it will support sector coupling through power to hydrogen conversion. In Denmark, we only emit 0.1% of global emissions. But by global support, via partnerships such as the one that we have with the government of Korea, we can do a bigger difference. In Denmark, we very much appreciate our cooperation with Korean stakeholders. We look forward to continue our fruitful collaboration, and I can only encourage you to continue to share learnings and experiences to ensure integration of renewable energy and develop the necessary solutions to the green global transition. Thank you for listening, and I wish you a very successful workshop. Thank you.
네, 감사합니다. 글로벌 녹색 전환을 위한 한국
Thank you. We look forward to a good partnership between Korea and Denmark for global green transition. Now we'd like to introduce senior researcher Hans Lyhne Borg, the Global Cooperation Department, Danish Energy Agency, who will give a presentation on the topic of brief introduction to the development of grid system relevant for renewable energy and current situation. He has experience in numerous areas, especially offshore wind power development, and please welcome him with a big round of applause.
Hello, everyone. Can you hear me? Hello, everyone. It's a great pleasure being here at this seminar. My name is Hans Lyhne Borg. I'm a chief advisor at the Danish Energy Agency. Just before going into the more technical elements of this seminar, I'll be providing a brief introduction to the development of the Danish power system relevant for renewable energy, including specific elements related to offshore wind. I'll also briefly present the current situation in Denmark with an overview of the 5 main focus areas, solutions in Denmark related to integration of renewable energy. The oil crisis in 1970s was for Denmark the starting point to focus on renewables. And jumping to the beginning of this century, the share of renewables was 12%. And as you can see from this illustration, the share of renewables has increased from 12% to 50% in the period from 2000 to 2020. Through this period, Denmark and Europe have continuously addressed issues related to the liberalization of the power system, meaning development of an electricity market and unbundling of activities related to transmission, distribution, and power generation. When we look back at the past 20 years, it's clear that the regulation and the market has contributed with efficient utilization of resources. The main categories of flexibility measures are listed here on the slide. We operate our thermal power plants more efficient in response to fluctuations in power production from renewables. We make sure that the least cost resource is used first through market-based operation of interconnectors with our neighboring countries. We've become significantly better at forecasting production from renewable energy. We are continuously trying to improve the sector coupling by exposing other sectors like heating, cooling, transport, and industry to the price signals of the power market. Recently, we've also looked into reducing barriers and improving the possibilities for demand-side flexibility. Denmark have installed wind turbines since the 1970s. Since then, the turbines have grown significantly in size and numbers and reduced the cost for wind power. As Uffe was saying, the first offshore wind farm in the world were installed in Denmark in 1991. On this slide, you can see the various offshore wind farms in Denmark. Today, we have in Denmark 15 operational offshore wind farms and a total installed capacity of offshore wind in Denmark of 2,300 megawatts. We have a number of planned offshore wind projects in the pipeline, which is expected to add a capacity of 4,000 to 5,500 megawatts. Here's provided an overview of some of the main offshore wind farms in Denmark with timing for commissioning, capacity, voltage level, and some of the learnings. The latest offshore wind farm, called Thor, went through an auction towards the end of last year. This will have an expected capacity of 1,000 megawatts, and the bid price was what we call a zero bid. It went to the minimum price, and it will be completely subsidy free and even provide an income to the state. Every successive offshore wind farm that have been installed have resulted in some key learnings that have made the next tender even cheaper and better, and also stability of the power system have improved. My key message here is the fact that we in Denmark have some very relevant experience and had a number of key learnings, and we are happy to share these learnings to help accelerate other countries' energy transition. So how have the power system and regulation changed to allow every increasing share of variable renewable energy? I've divided it into 5 focus areas, solutions that I would like briefly to take you through. First of all, considering grid codes, there are a total of 8 published network codes and guidelines that can be divided into 3 code families: codes and guidelines for connection, market, and operation. Network codes are a set of rules drafted by the European entity ENTSO-E with guidance from Asia to facilitate the harmonization and efficiency of the European electricity market. Each code gives transparency to the requirements and is an integral part of the drive towards an internal energy market in Europe to meet the Union's energy objectives. Looking at the market design, the efficient integration of 50% wind and solar generation in Denmark is to a high degree dependent on the dynamic and liquid properties of the wholesale market, with a day-ahead market as the primary market and the intraday market enabling bilateral trading. Liquid markets make it easier for the market participants to be in balance at the hour of delivery and ensure less work for the independent system operator for system operation and balancing. Today we have single day-ahead coupling across most of Europe, and in the near future new platforms will also enable cross-border trading of balancing services. Besides markets, it's also essential to have well interconnected areas. Denmark have continuously expanded exchange capacity with neighboring countries. This enables us to buy cheap hydropower from Norway and Sweden when the wind is not blowing in Denmark, and vice versa. Will it enable Denmark to export wind power when we have more than we can use ourselves? By the end of 2022, Denmark will have a total capacity of 10 to 11 gigawatts of interconnectors to 5 different countries, and we are continuing to expand. Flexibility has been key in securing increasing share of variable renewable energy. In relation to the thermal power plants, new market structures incentivized more flexible operation, and the combined heat and power plants of the combined heat and power plants and provided better abilities. This means faster ramping rates, lower minimum output, shorter duration to restart the power plant, known as warm start, and possibility for overload. In the graph here, you see a snapshot of the correlation between the power output of a large combined heat and power plant and the hour prices of the day-ahead market. And it clearly shows that the combined heat and power plant reacts to the price fluctuations. As mentioned, flexibility is important, but limiting the need for flexibility is as effective as increasing the flexibility of the system. The continuous development of forecasting and scheduling system has been a central tool for reducing the system's need for flexibility in Denmark. By having accurate forecasts and coupling these with real-time measurement, the need for sudden increased amounts of flexibility through balancing has been limited. Another important focus area and solution to ensure integration of variable renewable energy. Turning time all the way back to 1973, Denmark was hit by an oil crisis, as mentioned in the beginning, that limited our import of oil. We were highly dependent on oil, both for electricity production, heating, and transportation. More than 99% of the energy supply came from imported fossil fuels, mainly oil. The crisis was so bad that during the winter of 1973 to 74, we needed to implement car-free Sundays in order to be able to have enough oil to also heat our houses. This is a photo of a little boy playing in the middle of a street on a Sunday afternoon. This street was normally one of the most busy streets in Copenhagen, the capital of Denmark, with lots of cars. In the 1970s, the oil crisis forced us to change our perspective on energy and the power system, as climate change does now. Thank you for your attention.
네, 감사합니다.
Thank you very much. Now we would like to hear about the Danish energy system based on renewable energy. We would like to invite Senior Engineer Kwan Jun-bum from Energinet. Mr. Kwan is joining us online right now. Please welcome Mr. Kwan with a big hand.
보이시나요?
Can you hear me now? Can you see my slides? Yes. Good afternoon. Such a pleasure to meet you. I'm Junbom Kwan, Senior Engineer at Energinet. I've seen the list of participants, and I can see that we have audience from diverse fields, including the policy-making institutions. Today, I'll talk about how Danish has developed wind power and some of the interactions that we went through in Denmark in this journey, what kind of challenges we experienced, and what kind of things that we need to pay extra attention to going forward. And this is going to be quite technical, so there might be areas where it might be difficult for you to understand, but if you have any questions afterwards, please feel free to ask me any questions. So let me briefly introduce myself. I have worked in Korea briefly, but after I received my PhD in Denmark, I've been working in Energinet for 6 years now. And I've participated also in another offshore power plant design in the US. My main responsibility at Energinet is carrying out projects and analysis for renewable energy integration projects. And I'm also working at HVDC projects linking the neighboring countries ranging from the Netherlands and the UK. So this is my agenda. So I have concentrated a very long presentation into 45 minutes. First, I'll talk about how Energinet is providing analysis for stability of grid operation. We use RMS EMT tool for that, and I will share with you the simulation model and actual cases of analysis, how we can use this data for forecasting, and how this can be applied for renewable energy installation, and some of the actually 5 case studies related to some of the challenges we experienced in this area. As you might have been informed before, Denmark is planning to build 2 energy islands. We still need to finalize and prepare all the technologies needed for the islands. But let me share the issues that we are tackling at this moment. Before we go into further details, let me briefly introduce you to the grid in Denmark. It is quite different from the Korean situation. Our Korean situation is often said to be similar to the UK because China and North Korea, we are almost like an island, like the UK, but Denmark is different. Denmark has DK1 and DK2, 2 main synchronous areas. Denmark has a very small population. It's only 1/10 the population of South Korea, only 5 million. Therefore, the peak load is relatively small. It's between 8 to 9 gigawatts, and this is not updated. Now it's between 8 to 9, and at a high level, this DK1, the red cursor, is synchronized with Germany, and DK2 is right here. This is where Copenhagen is to the right. DK2 is synchronized with Nordic countries. So DK1, located to the west, and the west and the eastern parts are not synchronized. And for synchronization, there are 600 megawatt HVDC for connection right here. And we have AC connection with Sweden. And to get power supply, we have HVDC with Sweden and also another HVDC connection with Sweden, Norway, and then with the Netherlands, we have another HVDC. Although it's not in the picture, there is another HVDC called Viking Link with the UK. This is the world's first underwater cable link. Offshore power for now is they're mainly concentrated in the western area. They have 800 megawatt offshore wind power generation complex here. There is Enholt, 400 megawatt near here. And 2 or 3 years ago, there was another project that was completed, and this is the system that is in operation now. This provides simultaneous connection with offshore power through HVDC. So this is connected to Germany. HVDC link is here, and on top of that, DK2 also is synchronized with Nordic countries, and they need HVDC here. And HVDC is also connected to other AC technologies. For curtailment or other scenarios, Denmark has connection with neighboring countries to sell and get supply of power from neighboring countries. There is a lot of HVDC installed. So there are strong grids and weak grids. Strong grids are rather conventional systems. So there's the coal power plants or hydropower plants. And Korea has a lot of nuclear power plants. These are the basic synchronous generators. And on top of that, because of the high inertia, this will not have a negative impact on the frequency. But as we are trying to achieve CO2 reduction, we need to phase out coal power plants. Therefore, synchronous generators will also be phased out. In the case of Denmark, they used to have a lot of this, but now they have only 3 or 4 left, especially in the western area. In Copenhagen, they have more of this, but 2030, 2035, they're going to phase these out and go for full inverter-based system. But there are various challenges along the way, and the biggest problem is the inertia will be reduced. And on top of that, and the short circuit power will be reduced as well. But let me share the details of some of the challenges we face here. In Denmark, when we are carrying out such projects for offshore wind, there are 3 main stages. Before I go into the details, I want to emphasize one thing, and that is, in the strong grid, analysis was not so important in the strong grid. So in other words, you could hire a consulting firm, and whenever you need to install a new synchronous generator, all you had to do was, since this did not have a major impact on the system, but as we go for weak grid, even the smallest accident could be a big threat to the entire grid. One HVDC, if it suffers an accident, it can have ripple effects dozens of kilometers outside. So it could create a series of accidents. So when you're dealing with analysis tool or simulation model or data exchange with any vendors or manufacturing companies, or data exchange with offshore wind power generators is going to be really critical. And based on the accuracy, the role of the power transmission company will become more important. So let me come back to this slide. There are three major stages: EON, ION, FON. EON stands for Energization of Operational Notification. For major photovoltaic project or wind power project, there is the energization stage, and then the next stage is interim operational stage. And when you get the license or approval for all of this, the operator can get their wind power connected for test. So all the data that we need, such as dynamic, steady record, other various simulation models need to be validated here. And when they're tested okay, then we can give final operation notice. The most important area is this red area. From the start of the project to energization, like cable or converter, such passive area will not be a source of major problem, but for interim operation for offshore wind or PV power operator, when they have large scale grid and add the grid for test for final approval, this is an area that requires so many diverse studies, and this requires a lot of simulation models and data as well. If the data is not accurate enough, then it would be very difficult to have system level analysis. So I have prepared some case studies that have occurred along this red line. The first case study I would like to share with you is Krieger flex system. Krieger's flex system, back to the original map that I showed you. This is where it's located, near Copenhagen. And from Biabisko here to Berlin in the northern area of Germany, all of that area is linked through basic cable. This is world's first HVDC connected offshore wind project. And Krieger's flux system has 600 megawatts wind power, and there was also 400 megawatts existing offshore wind in Germany. There is a major offshore converter here, and it leveraged changed the voltage of existing offshore pipe. And to the east is Denmark, and there is an island here, and this island is not synchronized with Germany. So they have back-to-back HVAC, and they synchronize the frequency. And please, this is the next slide for HVC and offshore wind connection. These are some of the oscillation issues we experienced. And this occurred during a commission period. For offshore wind farm project, the biggest challenge tends to be that if you have only one HVAC, TSO can provide grid-related information, but as we go for weekly review, we have to consider the impact on wind power, like HVC control coordination. We will be seeing some new challenges. This is the problem we experienced. The Krieger's flags back-to-back HVC system is jointly shared between a Danish company and German company, and these three all have different owners, and this is a very weak system. And at first, we tried to reduce the grid, and we provide that to HVDC vendor. That's how we tested the stability dynamic at first. But when we actually went to the site for commissioning, between HVDC and offshore wind, there was a lot of intervention. Between Baltic 1-2 offshore wind power operator and the another areas operator cannot exchange data because of other issues such as patents. We used the generic models and they're not so effective anymore. And one of the problems we face is how the developing companies and the turbine developer companies can continue to exchange accurate information. And to your left, it will show you back-to-back HVDC system and AC line. And this is based on grid-forming converter system. This system itself is based on a long marine cable, and they have grid-forming technology. Grid-forming has very tight controller. And Nordic countries and frequency, based on their frequency fluctuation, the power can fluctuate plus minus 10 megawatts. And that's what we observed on site. We originally did the simulation. We should have been able to predict this, but our dynamic model was not accurate enough to predict this. And between other power generators, we could not share data effectively. So we could not predict this in advance, but in the commissioning stage, we've gone through some tuning to resolve this issue. This is a similar problem. So between active power and non-active power, there was an erroneous controlling tuning that led up to plus minus 200 megawatts. And HVDC converter station, Baltic Wind Farm, and Krieger Flags, they have created some oscillation. And through data exchange and based on the role of TSO as a mediator, there has been a lack of mediator role. Through data exchange and through more highly precise dynamic frequency model, and we use a lot of cabin incubator, but we did not use an equivalent model, but we expanded system level model, and we realized that such data needs to be exchanged. This is another case study. This is from Krieger flag to wind farm issue. This wind farm is about 600 megawatts, This is a very long AC cable and all the way from Germany. And for Kriegspflag connection point with the offshore power, this is the area we came up with based on our calculation. So this was a very weak connection. Based on this situation, we came up with, we have experienced such oscillation. This oscillation based on HVC operation point can be highly variable. And we did system level simulation for analysis. And we worked with the offshore wind power generator company. And we have installed active filtering. And during the interim operation, we resolved this problem before we went to the final operation stage. And next, this is something we have observed in the test. Energinet has a lot of system plan. We have the grid plan. Every 2 or 4 years, we carry out actual tests. If there is a major blackout in the western or eastern area, how is this going to be recovered in connection with the neighboring countries? We test that, and this is called SCARAP 4, which is an HVDC connected with Norway. And as a part of that test, we have done the analysis. This is the scenario. We disconnected all the grid from HVDC, and Volvo is the 4th largest city in Denmark, and they have overhead line and cable connection with the city. Soft energization, and through that, all the power line has been energized. And finally, there is a big power generator, and providing power to this generator is the goal of this scenario. But the power generating company did not give us the final approval, so we could only test with the recovery based on grid forming model. This is the simulation stage before we did the on-site test. In the analysis phase, we tested various interactions and oscillations. And as you can see, between 1500 to 1600 oscillation took place, and stepwise energization. We saw oscillation. And this is the manufacturing converter of Skega converter, and black start function here is not frequently used. It's used only when the grid goes in blackout. So we used the filter to resolve this issue. And SK4, there's SK123, and they are LCC-based HVDC. They're a very unique system. LCC HVDC has a lot of passive filters installed. And by using the passive filters, such oscillation can be dampened and then energized. However, in the actual test, This is the actual measurement we saw on the site. It's around 10 hertz oscillation, and we observed 10 hertz oscillation. We have various ways of analyzing this. Impedance-based analysis was used to simulate the impedance for the grid to see if the actual oscillation is appropriate or detrimental. And through coordination and communication with the manufacturing company, we have fine-tuned such scenarios every day. This is a very unique situation scenario. So we sometimes change the protective setting of oscillation. And as you can see, voltage source converter, or there's this weak grid, and such inverter-based system can create a lot of frequency-based interaction, and based on the size of the frequency or interaction, they can have different ripple effects, but they can trigger or they can create other interactions with neighboring inverters, and they can create some other ripple effects. So for each stage of analysis, TSO had to play a very important role. The next case is based on the latest technology of voltage source converter. Although this is not related directly to the inverter, this is based on harmonic amplification in our HVDC power system. In Korea, I heard that in the Western area, they are going to have 8 megawatt HVDC, LCC HVDC, and Denmark has a lot of expertise in operating LCC HVDC. But recently, we have experienced a high frequency issue that we could not predict before. Most of the offshore wind is going to be located in the western coastal area, and western coastal area is going to create a lot of renewable energy, and active power will be created. And in order to accommodate that, we need strengthening of transmission line. Also in Denmark, in the western coastal area, they are building a lot of lines, and most of the people here, well, I believe it's also the case in Korea, but there are a lot of vacation homes in the western areas of Denmark, and many people would not like having this kind of power transmission lines around their house. So we want to install cable, but cable also has a large capacitance problem. So it could create a lot of oscillation. And when we talk to the residents, and only 10% of the areas could use cable here. And as part of that issue, as you can see here, in the western coastal areas, there are various lines being built here, and also in the eastern area, they have to build lines. And as part of that, Aarhus is the second largest city in Denmark, between Aarhus and Jylland in the eastern coastal area. Between these two areas, they are going to replace the existing lines with a cable. It was a very short distance, just 8 kilometers, but replacing that with a cable, I'm going to remind you again. ACC, HVDC, we have one in the north, one in the middle, and one between these two areas for synchronization of frequency. And we have another HVDC called Contact with Germany. We have many HVDCs, and these two HVDCs, and between another one, some of the long lines have been replaced with cables, and then high frequency has been amplified. And we have actually witnessed a lot of amplification. LCC HVDC operation point or reactive power, active power, triggering point. Based on the changes, this could have a lot of ripple effects. The problem here is that we observe ICC standards, and general households, in the blinking of the light, or this will also cause problems using home appliances and cause blinking of house lights. But by expanding renewable energy, of course, we need to expand and strengthen the power lines, but residents are against having more lines, so we are using cables, but oscillation point at HVDCs, when they meet with high frequency issues, this will create amplification of high frequency. And when this goes above 1.5% limit, we might have to install more filters or other ways to reduce this problem. Energinet has a lot of expertise in identifying high voltage issues. Between Mulund and Sjælland, there are some substations, and we have observed and measured high frequency. And using the various analysis tools, we concluded that we will install passive filters in certain areas to reduce the high voltage. This is not limited to LCC HVDC. This is also related to array cable that are installed generally for offshore wind and long marine cable. Oscillation analysis is going to be very important. And when they synchronize with the 11th harmonic and 10th harmonic, it's going to create a lot of amplification. It's TSO's responsibility to analyze this precisely so that they have accurate understanding of what kind of ripple effects this will have down the road. And in the eastern area, they have this 400 megawatt inverter. It's not shown in the PPT slides. And the C cable, array cable, can create 11th harmonic frequency, and ACC, HVDC. Of course, they have the filter, but LCC, HVDC, in the next 5 to 10 years, they will need some more tuning. And if they are not tuned precisely, or because of the operation point, if there is amplification of high frequency near the Amhort wind farm, the residents actually suffered from high frequency, and they have registered a lot of complaints. Next is something that we have experienced recently. Fortunately, we did not experience a blackout, but it was a very serious accident. We almost had a similar blackout like the UK, but fortunately, we were able to avoid that. we call this DK2 incident. DK2 is in Shelland Island. This island is linked to Uland Island through HVDC at the substation, and it has AC connection with Sweden, and VJS substation has HVDC connection with Germany, and Cleese Flux system has this substation that has back-to-back connection with Germany. This accident in the eastern and western parts of Shelland, they have this meshy grid, but these two lines are the backbones. This VJS HBI transformer VJS, these are the main lines. When they go down, the 400 kilo backbone between the western and the eastern region will be decoupled. This is the accident. Near the substation, there were a lot of farms, and there was a fire in one of the farms, and the fire spread out to the power line, and the power line the first trip, when the line first tripped, ACC, HVDC recovered from fault. There was no problem with the recovery, but there was the fire spread farther and farther from HC to VJS. The power spread out, and this line went trip. And in Shelland, between the eastern and western parts, these two areas have been totally separated. And because of this incident, as you can see, these HVDC tripped, and DK1 HVDC also tripped, and synchronous condenser also tripped. So it was a cascade of trips. And Shelland grid was designed for expansion of renewable energy, and it was becoming weaker and weaker, and frequency stability fluctuated a lot. Of course, we have recovered a significant part of this line as the two line tripped, two HVDC tripped, and condenser tripped. This is the actual Copenhagen area, the capital of Denmark, that 1/5 the population of Denmark lives in the Copenhagen region, and they get power supply from Sweden and Uland. And they had LCC HVDC line, but it tripped, so the power supply has been cut off. If they did not have AC connection, the entire Copenhagen area could have gone black. So what I want to emphasize here, I will skip this area. As a TSO, what can we do to prevent such accident? Energinet has is replacing a lot of old cable or line, and when there is new offshore power or HVDC added to the grid, we do a lot of simulation and analysis. And when we are doing simulation, the important thing is it really close enough to the actual case? We have used a lot of RMS databases, but RMS databases Well, Energinet is proud that we have relatively advanced RMS system, but the system that had the accident was a weak grid, so we could not do simulation based on RMS. The models we received from vendors and developers were quite simplified, but what we need is EMT model that has full trigger function. When there is accident, we can compare this data. The blue line is the actual measured line, and orange is EMT, and green is RMS. The RMS model, we could not use that for simulation for the accident. And weak areas, subsynchronous oscillation interaction issues between converters, we saw interference and how accurately that can be expressed in the control model, and how the oscillation model can show the accident or trip. That is very important for system level analysis. And for cable or line expansion, as the renewable energy is expanded, we need to have an accurate analysis of its ripple effects. What we realized from this incident was that RMS model can be highly inaccurate when it comes to weak system. So what we are working on now is EMT-based system-level simulation. There is the bandwidth that can cover both the RMS and EMT, and strong grid-based system, synchronous dominated system, they can the RMS was enough. But in the inverter system, we need to have more EMS type model. And Australia had another accident, and the UK also had an accident. They were all similar accidents. In the RMS environment, we cannot have accurate analysis of weak system, and the other TSOs are now accelerating the introduction of EMS system. In the EMT model, regarding interaction system, we can do control loop interaction system, nonlinear functions, and they are becoming increasingly important in weak grid, and they are usually simplified in RMS model or not included at all. So as a grid operator, we have no way of accurately analyzing this. But as we expand renewable energy, cable and lines will be expanded and strengthened. And the impact on the lines, that needs to be accurately analyzed. So I might be repeating that. The RMS model, we use this. It has a very big database accumulated over a long time, but in certain weak grid system analysis, the accuracy was low. So currently, we are using other EMT tools to develop system-level models, and Uland and Shelland, the entire grid can be built on EMT for simulation. So from planning to entire analysis, we are going to do that based on EMT system.
EMT 모델에서는 이제 뭐 주로 이제
In the EMT system, the biggest problem we have is the calculation capability, simulation time taking a long time, but computing capability has been enhanced greatly. So we think this is not going to be a major problem. So these days, we are validating the EMT model with the RMS model, and we are capturing the accidents and recreating that on EMT, and to see if what went wrong. After we build all the database, we are going to use the EMT model for wind farms or HVDC or other offshore power plants. So EMT is going to be the main tool for analyzing all this down the road. Another point I would like to make is TSO. I believe KEPCO does not separate TSO from DSO, but in Denmark, there is a separate organization for DSO. DSO is building a lot of PV power, and when there is a trip or fault, based on the scale, it can also have a lot of impact on TSO. It can create oscillation or trip some protection relay. So we need to also include DSO in our simulation model to improve the accuracy. I think I'm behind time. This is key takeaways. The summary of the key points. In analyzing the weak system, HVDC or connection with the offshore wind, database analysis is becoming all the more important. And if we use using a conventional source for analysis is no longer valid, we need system-level development. And between the wind farm and inverter-based system, we need to have an accurate analysis of interference to prevent the risk of having a major blackout. And we are working very hard to resolve this issue. And in the second presentation, I will talk about system strength. We cannot explain everything through short circuit power, but Korea does not have ACC connection or HVDC connection with another country, but neighboring countries around Denmark are all connected with each other, so frequency and frequency stability can have impact on neighboring countries, and based on our experience, short-circuit current-based system frequency stability seems to have more impact than short-circuit power impact. This is related to inertia. Frequency drop can happen more frequently, and when there is a trip, frequency can go down or transient can fluctuate more. We have actually seen that happen, and in order to recover from this, from the planning stage of the grid, we are looking into various alternatives. So, Min-sun, how am I doing with time? We were planning to have a 15-minute coffee break. So we can have just a 5-minute coffee break, and then you can continue with the remainder of your presentation. So this is coffee break time. So enjoy your coffee break. You can go to the bathroom or have a drink of cold water.
감사합니다. 네, 이제 휴식 시간이 거의 끝나가서요.
Now the break is almost up.
네, 이제 휴식 시간.
Ladies and gentlemen, we are about to begin. Please be seated. Time really flies. Can you see my presentation slide? Just a moment. Let me give you a housekeeping announcement. Can we see the presentation slide, please? Those of you who have parked your cars, once again, this is a housekeeping announcement. It's free of charge. And then after 3 hours, you have to pay the money. So once again, please make sure. Can you see my presentation slides? Yes, we can see you now. So let's begin the presentation again. Are you ready? So from now for the next 45 minutes, right? I can begin my presentation. This time, we are going to have a Q&A session. So I know that you have prepared a lot of materials to make a presentation. We don't have much time, but if you have any questions, you can raise your hand and then we can hand over the microphone. So please speak into the microphone if you have any. Okay, so may I begin? Yes, please go on. Before I begin my presentation, Dr. Lim has asked me a question. And during my previous presentation, what I wanted to say is that
Using the inverter does not mean the grid would be weak. That's not what I'm trying to say.
개통 운영
The role of TSO and the offshore wind or PV power generators, they need to communicate very closely. And the TSO's role is going to be very important. And when it comes to weak grid, there are certain problems that need to be prevented, analyzed, and predicted, and TSO needs to play a very important role. And system level analysis is quite critical.
so based on the analysis, HVDC or a large-scale controller planning or a renewable energy needs to be strengthened. All the necessary cable or filters or other installation plans needs to be well analyzed. So no matter how many inverters you have, you wouldn't have any problem in operating that. And of course, that's what Denmark is aiming at. That is why we are paying a lot of attention and making efforts for analysis. So regarding your questions, I hope my answer is sufficient. But if you have any questions, please ask me after the end of my presentation.
발표를 이제
So let me continue to make my presentation. So I only have 45 minutes. And now regarding the energy hubs, let me tell you what this is about. So the Danish government, they have issued directives and there is a Danish climate agreement.
이제 거의 확정이 됐습니다.
And they have finalized the energy hubs. So Denmark is going to have energy islands or energy hubs. And they are located in North Sea to the west of Denmark. It's going to be between 3 to 5 gigawatts initially, but this will increase to almost 100 gigawatts because they have so much potential capacity. And we are now in the preparation phase for that. And there's another energy island. It's kind of like Jeju Island for South Korea. It's called Monolum. And it's Denmark territory, but it's not connected to Denmark through power line. This island is getting AC power supply from Sweden, and this island has a lot of wind power resources. And initially, there will be 3 gigawatt offshore power plant on the island, and this energy will be sent to Denmark, Sweden, and Germany through HVDC. This is another picture. 3 gigawatt offshore wind is going to be installed by 2033, and it's going to be more than 1 gigawatt. This offshore power plant is going to be linked with the Netherlands, Belgium through AC cable, but we have not finalized this mode of connection. It's going to be either HVDC or AC cable, or a mixture of both. And the power will be traded between these countries. This is Bornholm Island connected to Sweden, and there will be 3 to 5 gigawatts of offshore power plant,
근처와
and it will be HVDC connected with Copenhagen, and also Sweden, Germany, Poland could be connected for power trading transactions. And this island has the vision of become energy independent island, and after the offshore power plant installation, they're going to cut off the AC connection with Sweden, and the offshore power wind will supply all the energy needs for the island eventually. So I will skip this part. And this energy island between Denmark, UK, North Sea wind power area countries are all interested in this project. This is slightly different from existing offshore wind farm. How is this different? What kind of technical issues do we have? I'll briefly talk about that. This system, Cleese flux system, is the basic system. This is the world's first HVDC wind connected offshore wind farm, and we have learned a lot through this project. We have learned a lot about potential interaction, how the AC cable is operated, and how we are going to exchange information with the other stakeholders. So we have learned a lot and built a lot of experience. This project could be a reference for North Sea wind power hub and the Bornholm Energy Island. These energy islands is likely to have a very similar structure. They have AC cable connection, but it can change to HVDC and offshore power transmission to other countries. Whether the frequency stability will be considered. Cleese flux system will be a reference system for many of these questions. Through this reference, we believe that this energy island will become a very complicated system, and the main technological challenge will be whether AC system or DC system would be the best, how to coordinate the protection system. These are major technical challenges. This is the Cleese flux system. And these 2 substations are located in the southern area of Sjælland, and 260 kilowatt system will have 180 kilometers of connection. This is offshore, and 600 kilometers of wind farm. and converter and system connection with Germany, and HVDC back-to-back system for synchronization. This system might look simple based on the diagram, but it needs a master control, and how this master control will communicate, what kind of command the TSO needs to provide. This is a very complicated process, and we believe the Energy Island is going to have even more complicated system because we are planning to have 3 to 10 gigawatt system. So based on the experience that we have built from this project, Energy Island, how is this different? Energy Island can be defined as follows. It is going to be a highly independent system, energy system. It's going to be 100% power electric system. And synchronous condenser for offshore wind can be installed, or other devices can be installed for enhanced stability, but they're now in the research phase. We do not have the final solution now, but it's going to be 100% power electric based system, and there will be multiple offshore power operators, and 1 to 500 HVDC will be supplied by other vendors and stakeholders need to exchange the data, but what type of data should be exchanged is going to be a technical challenge. And this energy system also needs to be interconnected. And we are considering the other alternative systems. And from the beginning of the offshore power plant, it really takes 5 years to go to the final operation phase. So unless we do parallel of 3 megawatt, but if we have sequential phase, then it's going to take at least 10 years. And the wind power resources can be enhanced, so we can continue to build more grid or more power plants. So how we are going to build an expandable power generation system is another challenge that we need to tackle. The main issue here is it's going to be very costly to build the infrastructure. So from the beginning stage, we need to consider expandability of the system. And when it comes to the control and stability of the system, energy islands are 100% based on power electronics inverter system, and there is a lack of international system for that. And when there is an offshore power fault right through or other offshore, grid codes should be met. And from offshore to onshore, the existing offshore wind power has a lot of international standards, but here there is no international standard. And because of the challenges in data exchange, we call this interoperability. Interference problems between converters can occur. And let me talk about interoperability. And this is the structure that shows Denmark, Germany, and various countries are linked through HVDC and to energy hubs. And there will be more than 5 wind power plants, and power operators or wind turbine manufacturer, they can all be different companies. Vestas could be the turbine manufacturer, Vattenfall could be the operator, Siemens Gamesa could be the turbine manufacturer. So various combination can be made here. So it's difficult to exchange data because this is related to patents and they're competitors to each other. They're unwilling to exchange this data. And same thing for HVDC. Hitachi, ABB, Siemens, these are the main companies and they are not willing to exchange data. But because of the various interaction issues and other incidents that we have experienced, these vendors and developers must exchange data, and TSO should create an environment where such data can be exchanged. France, RTE, National Grid, various TSOs in Europe are experiencing the same problems. So the inverters, the coordinating the interference between converter is becoming increasingly important. So there must be some protocols developed for data exchange. But based on ENSOE, we are hosting a consortium called Interoperability, and main ESOs of Europe are hosting this. So vendors, power generators, turbine manufacturers are coming together in the consortium to discuss how the data can be exchanged and how the interoperation of converters can be smoothed out. And modularity and interconnection are different issues. Offshore power system, when they're expanded, on top of these three, if it is finalized to be around 4 or 5, how the master will control this. And of course, plug and play is the best scenario, but this is not maximum grid. So plug and play will be very difficult to be realized here. So TSOs need to be coordinated and communicate very closely here. And we are doing a lot of analysis for this purpose. And for control and stability, offshore, we are talking about whether we should do grid forming for offshore. Grid forming is about controlling the voltage and frequency for offshore wind farm and PV farm. They are like grid following. So power generator can, TSOs and DSOs can control the frequency, and power generator can follow the voltage and the frequency. But in the offshore power wind generation, there is no device for that. So what kind of structure needs to be built is going to be a very important issue. And these days, whether we are talking a lot about whether we can do grid forming for offshore wind. We are in the R&D phase, and we are talking to various vendors and offshore power vendors. This is not in a mature state now. Now, considering that we are going to do grid forming and grid following for offshore farm and synchronous, do we really need battery system for grid stability? So that's another important technical issue, and we are doing a lot of feasibility study for that. Another issue here is, as I've said, AC coupled system. AC can be connected to short or long C cable, and when HVDC cannot be operated anymore, the entire wind farm energy will go only to HVDC N-X situation needs to be considered in our study. And we are closely talking to vendors about whether AC couple has more advantages. And also based on the dynamic situation, characteristics of the stability of the grid, we also have to think about modularity, interoperability. So whether which grid has more advantages. So we are talking to 3 major vendors about these issues. Whether we are going to go for AC or DC is being discussed now, but there is a lack of international standards now. And European TSOs have not finalized the clear grid codes. They are called DC grid codes. They have not figured out how this code should be developed. And the vendors are very curious about what kind of code TSOs will develop. Based on the meetings that we have had so far, major vendors are very well prepared. DC protection coordination, they already have a lot of technologies, but each TSO, are they ready to go for DC grid? What kind of this grid code should be applied here? So we are also developing grid code in parallel. This is a huge system between 3 to 5 gigawatts. It can go up to 10 or even 100 gigawatt. This offshore wind system, when they're integrated with the systems of other countries, what kind of changes can take place and what kind of impact can we have on the other European countries? Now, based on 3 country connected scenarios and 2 countries are not connected, can one country import all of this offshore wind? But if there is a trip, there will be 2 to 3 gigawatt of loss, which will create very big fluctuation. So we also have to do system level analysis of its ripple effect. And there are RMS based analysis and EMT level system. We are also doing the analysis at EMT level as well. There are various issues, but because of the time, I won't go over everything. But if you have any questions, you can send me the question by mail, and I will answer every one of those questions. So let me move on to the second presentation.
잠시만요. 두 번째 발표
Please bear with me for a few minutes. I'm trying to open my second presentation file deck.
보이시나요?
Can you see my presentation? Yes, we can see that. Thank you. I believe I have around 25 minutes left. So I will point out only the most important points. During my second presentation, the message that I'd like to deliver to you is mostly Professor Chun Yong-hwan asked me a question, how Energinet evaluate the system strengths and what kind of methodology we use for the short circuit power. So these are the agenda that I'll be covering: introductions to short circuit calculation, what does it means, and also maximum and minimum calculation, and I will cover the handling increasing short circuit currents. We have an actual case in Denmark, and what kind of implication that Danish case has, I will explain about that. So let me begin with introducing the short circuit calculation. It's a very classic terminology. This is use of a short circuit calculation in TSO And we try to calculate short circuit current in general. It is designed of devices in transmission level. So if you look at short circuit calculation as an inverter system, wind power or PV mostly, and it can also have different meanings. There are things that you have to consider. So the terminology short circuit began to have a different application. At Energinet, in my company, we issue short circuit report. Of course, it's based on simulation. We have a different department that is in charge of the grid and power system planning, and they come up with different scenarios, and we review them, and then based on that, we conduct simulations, and then we publish report. The report has a diverse purpose. I'll give you example. For example, when we try to interconnect that, then vendor and developer, we need to tell them that our grid or our power system is at such stage, and when is the weakest time, when is the strongest time. We need to inform them, and also when we try to design, then we need to describe the severity of the overall current that a device can reasonably be expected to withstand, which applies to breakers, disconnect, and conductors. Also, breaker duty evaluation using the short circuit duty result. Breakers are determined to be able to withstand the fault it needs to clear with respect to X and R ratio. And to DXO, of course, DSO are connected to TSO, but we need to give them indications of relative classical system strength, and also short circuit calculation report should be sent to DSO. On top of that, DSO can come up with its own plan, and the grid connection project can be carried out. As I mentioned before, the impedance, polygon, and voltage, power, quality, all of these related with the grid connection project. We have a researcher and team in charge of that. And also EMT studies, we also have a huge simulation to analyze what is going on in this wind power. The methodology that we use can be classified into two. First, Texas TSO, EDICO, or other TSO use different methodology, but ESC line or SCR or numerous other ways. We are currently at stage of evaluating. We don't apply them yet. The methodology that we use is a very much classical methodology. It's called IEC planning. It's correction factors, and in a very conservative way, we calculate this. And there's another way, complete method. Each inverter, we come up with a load floor. So operation scenario, we have that, and then we calculate load floor instead of correction factors. Let me compare that. First, the short circuit current characteristic of conventional synchronous generators, where IP is short circuit surge current, and IK is a sub-transient short circuit current. IK is steady state short circuit current. So we try to understand whether it can be applied, what's the meaning of that, which are critical. In case of type 1 to 3 converters, the most of them are DSO connected and negligible. And also, it doesn't, in case of TSO, it doesn't have a huge influence, but LCC HVDC should reduce current according to operational characteristic to avoid commutation failure. And also, so-called short circuit current type 4 and VSC HVDC has mainly short circuit contribution. So it's a voltage circuit, offshore or PV, you can see that. In the beginning, when there is a short circuit current, the first peak is very difficult to predict because it happens in a microsecond stage, and overall, synchronous generator signage is not happening. So it shows a totally different tendency compared to converter, and it is also influenced by various other factors. So the area that we focus on is what happens after that. So in this period, it's difficult to predict, not purely sign, which is a huge difference with SG. And there is a need about 20 to 60 milliseconds in order to supply balance current up to 1.1 to 1.2 pu under any type of fault. So let me elaborate. Now, this is the grid following converter short circuit contribution. And you can see here that since converter filters are not able to hold big energy like rotating mass in synchronous generator, durations of IP is quite short compared to classical synchronous generator, and static current magnitude is determined by controller and grid codes. And you can see here on the left, typical short circuit current behavior of type 4 converters. So it can come back to the normal stage quickly. So the area of the dynamic is very short, and static we can easily reach. And here, static area 1.2 IPU. Yes, that's the method that we do. Now diving into the methodology, 2 to 3 years ago, we have always applied the classical IEC methodology, which is the planning, correction factors, etc. So we've done that, but now we are applying complete methodology. So it's based on the Germany grid code, and the complete operation scenarios is based on the load flow instead of the correction factors, and inverter-based generation includes uses of different iterations to determine the contributions. So we have the different time frame used to measure short circuit current characteristic in EMT model, where IP is short circuit surge current, and IK is subtransient short circuit current, IK is steady state short circuit current, and test condition for short circuit current characteristic of VSCS in EMT tool, test conditions for WTS, and test condition for HVDCS. So each vendors and developer, we tell them that when short circuit happens, the contribution is such and such. We notify them and we request the data, and based on the data, the system level database is being updated. Well, this one is very detailed, so I'll skip that. It's too complicated for me to explain, but one thing, the dynamic voltage support model is used to reflect the requirement of various grid codes to support the voltage in case of the fault with reactive current. The short circuit contribution is split up in two parts, the subtransient and transient steady state part. Now this one is a simulation result. We have only used IEC methodology, and when we do that, the contributions of the inverter, what it is, we try to compare that, and also when we do that in parallel with the complete method, what happens, we try to understand. So wind and PV, the contributions to the short circuit can be exactly and precisely calculated. So you can see here. This shows the type 4 wind turbine model comparison between EMT and static models, and based on the complete model, we have done the simulations. So maximum and minimum short circuit characteristic comparison of EMT and static WT model, considering different test conditions in table 1, RMS value of A, short circuit current, B, active current, C, reactive current. You can see that it really coincides. So existing wind farm or PV or other things, through the internal test based using EMT model, we can see see exactly what's the contribution to the short circuit. So we evaluate, and all the data are input in the RMC value, and then we conduct calculation. What you are looking at is a simulation result of the VSC HVDC model measurement at a different grid condition. Let's go deeper into the preconditions maximum calculation. What we really think about this is the scenario. When we think about 2040, we need to screen that. And at the stage of planning, what do we need to consider? Well, 2040 and 2050. Previously, Senior Researcher Hans Lyhne Borg already showed you the slide. This is what we are aiming at. And the capacity or the power of inverter, to what extent do we have to consider? And what if that experience short circuit, and how do we overcome that? Do we need to expand that? What kind of challenge are we going to face that we need to consider all of that? So the grid configuration, projected productions and consumption, and complete method with realistic load flow, we need to consider everything. So at the screen level, these are critical. So before we go deeper into the analysis, we have to look at diverse and different scenarios. That's what we are doing. And when we do the maximum calculation, synchronous condenser or central power plants, external grid, CHP, grid configuration, HVDC, VSC, in full operations, and wind and solar, all unit in service. Because of the intermittent characteristic, we based on our experience, we come with a scenario that wind and solar, they make a contribution of 50% because of intermittent characteristic. Then Denmark, Sweden, Germany, all of these countries are connected through cable. And based on the short circuit report or minimum short circuit, all kinds of scenarios we calculate so that, and we consider so that we can come up with the maximum calculation. Same thing applies to the minimum calculation. The previous one was a maximum calculation, but minimum calculation, when we try to calculate for the short circuit, when to the Germany it is connected, then what is the minimum calculation? We try to screen that. So we perform using complete method and C-factor approach using realistic minimum voltage, and then combination matrix. And this is our own terminology. And combination matrix follows minimum number of plants in service based on our system operational guidelines. So based on these, we issue annual report. This one is a little bit overlapping, so I will skip this. Then I would like to show you the result. Practically speaking, people say synchronous generator is about 7 to 8 PU. That's the contribution level to its own capacity. However, in the inverter, as I mentioned, 1 to 1.2 EPU, that's all, the contribution level. Based on the data, people say that if you install a lot of inverter, then the grid will be quite fragile. But as long as we have the coordination, data exchange, model exchange, TSO role, and accurate analysis, then you don't have to worry about anything. And grid stability can be secured, unlike what people say. As you have seen previously, 2021 is on the left. You can see here, short circuit is all green color. So what does green color means? Existing legacy, the cable, or everything. Short circuit current, everything is within our capacity to manage and control. But with expansions of the inverter, the major areas when the photovoltaic mega scale panel is established, or another link is connected, or on the western seashore area, a mega scale wind farm is established, offshore wind farm is established, what happens? In that case, we need to calculate the contributions and think about short circuit. So for that, we need to strengthen we need to plan alternatives. So through verifications of the scenarios, we try to expand the cable and we try to seek many ways to overcome any kind of challenge that we might be faced with. This data shows different things. It shows the maximum short circuit current between 2025 to 2040. Based on our analysis, you can see that KS or CASO, we call that, or the red colored dot area is a problematic areas. And from the renewable energy, this problem occurs. I shouldn't use the word problem, but should I say that the inverter, as it increases more and more, then the role of KEPCO or energy's role, we need to strengthen the system. It's critical, the system strength. As you can see here, Germany is a huge nation and its contribution all the way until 2040 is huge. But offshore wind or onshore wind compared to the offshore, onshore wind is low, but still the portion of PV, the contribution is increasing, you can see here. So PV or offshore, the area where it's connected or neighboring area, we need to carry a system strength. That's urgent. This one, I think I have mentioned several times, but the sensitivity, this is about the summations of the sensitivity study. The SC influence from the source are locally. Germany has a large influence in south, and wind has a large influence in the western part, and solar is spread throughout the system, and synchronous missions within 5-10 years. In the western part, a new wind farm will be established, and about 1.2 megawatt size of the wind farm will be installed. So we need to carry a system strength on the western part. And there are a lot of PV being established and introduced. So we have selected this area as a vulnerable or weak area. And Shelland, I have mentioned before, and this CREAX Plus system or huge PV farm will be installed. So the short circuit calculation based on the result that we do, we need to do the system strength in a very, very detailed way. For that, we need to do the calculation. So once again, for the system strength, we need to do the evaluation. And for that, we are also doing a lot of studies. So what I'd like to emphasize is there are many ways to conduct short circuit calculation, but accurate representations of short circuit contribution from inverted base system would be more and more important as power system is governed by inverters. And the best way to characterize short circuit characteristic is to use data directly from vendors as a part of grid connection requirement and the use of data to build up models in TSO's database. If it is limited to ask data to vendors for some reason like plants or HVDCs are already under operation, the proposed approach would provide similar result and give overview of short circuit contributions of vendor-specific models. The system strength issues are highly important to secure stability of power system, including protection equipment and power quality. However, high penetrations of inverter-based system does not always mean that the system strength deteriorates, since inverter-based systems are not able to contribute reactive and active current actively to support the voltage and frequency. That's all I have prepared. If you have any questions, please let me know. I'll do my best to answer those questions. Any questions from the floor? Or the area that you don't understand, please raise your hand. Yes, go on. Professor? Wait. Just wait until you get your your microphone. I am Chun Young-hwan, professor of Hongik University. Thank you for the great preparation. I'm sure that all the participants learned a lot from you. Thank you so much. I have 2 questions. Well, in case of Korea, compared to Denmark, the size is like twice bigger, but the peak is like 10 times bigger than Denmark. So if you look at energy density of Korea, simplistically put, we are 5 times higher in terms of the peak. And in case of inverter, once again, it's about 5 times bigger. You talk about the issue of the inverter, we can design filter, and then we can overcome this challenge. Then the interactions between 2, interaction between 3, interaction between 4, when it increases more and more, double, triple, quadruple, then what about the filtering interactions? They can also be, right? Then we need to consider filter interaction as well. And you talk about system strength. But realistically, how can we carry out system strength? In what way? Can you clarify what do you exactly mean and how do we realize system strength? Well, regarding your first question, thank you so much for asking that question and thank you for giving me the opportunity to make a presentation. I truly appreciate. Regarding your first question, let me answer. Yes, the issues that you mentioned, yes. Within European Union, all the TSOs, they are currently in progress. The first issue is interoperability. So in offshore, the PVs, for example, there is a photovoltaic panel being installed, 1 or 2. If it's installed, then the transmissions or distribution power of each TSO make a different result. I'll give detailed example. Some European TSO, they don't even recognize the challenge of that. They have never experienced this before, so they don't know what this is about. So they are taking approach of taking care of one by one immediately what's happening. However, the Energinet or Tenet or other TSO, they are recognizing these issues as difficult issues, and the role of TSO is extremely important, especially the coordination is extremely important. When TSO enters, the high voltage influence is extremely difficult and extremely important, and control interaction mostly is about 100 hertz. The control interaction that happen, even if it's below 100 hertz, when that happens, the active damping or passive damping, when that happens, then the next TSO, when it enters, the connections could also be different. So the first PV operator, if it didn't experience anything, but next PV operator could also experience difficulties, then who will be responsible for that? That's an issue regarding that. The TSO role is very, very important. The way we do, the approach that we take is as follows. So if the TSO is number 1 and PV is number 2, then all kinds of system models, as I mentioned before, the grid system starting from the connections all the way to the end stage from the A to Z, the model verification must be done between the models and data must be verified. And also the PV data are actually installed. What about the power plant control, PV control? Everything must be verified. And the second operator, when it enters, when there's an issue with the interaction, then from the TSO level, we need to analyze and we need to coordinate that. So PB number 1, PB number 2, when issues happen, we need to understand whose fault, who is more responsible. Is the influence of the PB1 is more is bigger, or PB2 is bigger? We need to analyze and verify that. And secondly, what I can say is that, what was the second question? Can you repeat the second question? Well, since I have the microphone, system strength, you keep saying that we need to carry out system strength. But what do you exactly mean by that? Can you specify that? What are you implying? And regarding the first question, what I'm worried about is when interactions happen in multi-phased way, I mean, one or two, yes, we can resolve that by using controller or filter. But when many multi-phased interaction happen, then how can we resolve that? So analyzing the interactions, we can understand the issues, but can we really resolve that? Identifying the issues, understanding that, and resolving that are totally different things. So that was my concern. Yes, I understand. Regarding your first question, let me add. Yes, the issues that you mentioned about the interaction, it depends on the coordination. So, number one, conducts active impedance, and the second, operator enters, and then when interaction happens again, who is responsible? We need to identify that. What are the reasons? We need to clarify the source of the problem. But as you mentioned, if the second operator are there and active ramping or other methodology has been applied to reduce these issues, but can they afford to experience these issues? Can they curtail these issues? Can they afford? Well, regarding that, TSO, there's nothing TSO can do that. Developer or vendor must be responsible to resolve these issues. So when interactions issues happen, then the only things that TSO can do is inform that there is an issue. And then vendors and developers, they need to understand whether they can resolve these within their capacity. Is it the functions of ramping? Can they add it, or can they utilize the other methodology controller? If not, then additional device must be installed. They need to identify that. For example, converter-based ramping methodology must be installed additionally or not. Very close consultation must be carried out. Well, I cannot say there's a concrete answers to tackle these issues, but as I mentioned numerous times, the role of TSO as a coordinator, as a data exchanger, and as long as we don't infringe the patent, we need to make sure the data exchange must be done properly. So that's the most important thing. Now, regarding your second question, how can we carry out system strength? Well, short circuit power capacity, from that perspective, we need to strengthen the voltage. So that's the best way to do that. But in doing so, LCC HVDC, we need to slowly being replaced with VSC HVDC. But as I mentioned before, in system strength, whether it's cable or other things, well, it's hard to do that. But cable is the weakest point because it creates issues and it gives huge impact. So we need to reduce the percentage of the cable because of there's an issue with the resonance. And when I analyze accurately the situation, the resonance caused by cable, or in LCC HDVC, the vacuum resonance, how can the system operator manage that? That's also important. It's very, very important. So it's a similar issues. You mentioned about interactions, but it's also similar issues. Power active use causes interactions, or because of the voltage, where does it come from, what's the issues? And we can definitely take different approach, but depending on the voltage, when the voltage happens because of the frequency, there's nothing we can do much. And frequency, according to the IEC standard, it doesn't recommend 100% reduction, because 100% reduction, when we do that, additional money will be spent. And also this happened because of the coordination in accordance with the IEC standard. Well, high voltage contributions by an operator is 0.1%, then that if it doesn't exceed the limit, then we allow that. But when the next operator enters, and in the background harmonization, when it gives some influence, and then we need to coordinate that, and based on that, we can allow the installation.
네. 네, 답변 감사드립니다.
Thank you very much for the answer. Now, that was a very long presentation, and please give a big round of applause to Senior Engineer Kwon Jun-bom. And we have last presentation. And now we are going to invite Senior Researcher Cho Jung-min from KEPCO Research Institute, and he will talk about inverter technology development for renewable energy.
네, 안녕하십니까. 저는
Good afternoon. I'm Cho Jung-min from KEPCO Research Institute. And we are running behind time, so I was asked to cut down my time for presentation. So I feel much more comfortable now that, I feel better, more confident. And today, I'll talk about inverter development for preparing for the expansion of DER. So I did not go into the details of inverter technology itself, but inverter is basically, as Mr. Kwon Jun-bom from Energinet has mentioned, inverter technology, there's grid follower, and grid supporter inverter, and in the future, there will be grid forming inverter. So there are many different technology versions of inverter. And GMI, grid forming inverter, has inertia problem. So the inertia issue has to be resolved through some kind of artificial inertia. So instead of talking about the details of inverter technology itself, I would like to talk about the expansion of renewable energy and what kind of efforts we need to make to accommodate renewable energy in our existing grid. This is my agenda. Well, we talk about climate crisis, and 2050 carbon net zero emission is something that we have heard numerous times. So this is a keyword that we should all be reminded of. So let me skip over this slide because everybody knows about this. This picture shows we are now in 2020, but this picture shows how the grid in Korea has evolved over time. 20 years ago, there was a large-scale centralized energy system, but 20 years later, in 2040, we are going to have localized energy system. Localized energy generation and consumption is going to be more prevalent by 2040. And now, distributed energy resources will become more important. So we are in the transition to distributed energy system. These are power generation current status in Korea, types of transaction and connected capacity. And now there is more power connected to transmission than distribution. And the bottom of left-hand chart shows the contract type. And between 90 to 100 kilo, the distribution takes a big portion. And in April 2015, this has been upgraded from 100 to 500, and REC has been given 20% weight. So rather than above 100, it takes big portion below 100. When we develop the monitoring system, I believe this portion should also be monitored. This is the DER, and this shows the feeder hosting capacity for DER. And there are a lot of complaints about this power not being connected to the grid right away. And when we connect DER to the grid, what kind of factors determine the capacity? Well, there's the thermal limit and voltage quality and protection coordination and reliability and safety. These are main determining factors. In order to connect DER, we can focus on thermal limit and voltage quality. And in the later slides, I'll talk about hosting capacity. Without adding additional facility, we can use the existing grid and accommodate the renewable energy without creating any negative impact. So that's called hosting capacity. So these are the two factors, thermal limit, voltage quality, that will determine the hosting capacity of existing grid. In Korean grid, we need to do the voltage management for connecting with DER. In the past, from the power station, there was one-way transmission, but we are also seeing reverse flow of power, and that increases power voltage. This can be local problems that's more frequently found in distribution rather than transmission, and that sometimes causes dropout of inverters. The point that I'm trying to make here is that by managing the voltage, we can accommodate more DER. And what are the technologies that will enable us to do that? There are three methods. First is connecting new DER and smart inverters. Grid support functions can enable DER to be connected. I will talk about this in detail later, but grid following, grid supporting, and grid forming, out of those, overseas countries or cases, including the Danish grid, they already have smart inverters. But in Korea, we do not have smart inverters yet. But last year, Smart Grid Association has established a criteria for smart grids. In December last year, KEPCO has established the connection technology standards, and May and September this year, we are going to come out with KS standardization for grid, and Korea Energy Management Corporation is working on these standards. So grid support functions, I'm not limiting to the voltage management, but there's the volt var, Q set point, fixed power factors. Of course, we also need to use inverters. Inverters can contribute to voltage management and frequency watt P limit. These are areas that can impact the frequency. So such smart inverters functions will be needed in those areas, and we now have technology standards for this. Second, I'm talking about existing inverters, and existing inverters voltage should also be managed. And for that, we are using monitoring control device, and smart inverters functions can be used based on autonomous functions, and existing inverters do not have smart functions, so we can build control and monitoring functions so that the inverters can be embedded with the grid control so that they can function as smart inverters. But once we introduce smart inverters, we are going to get rid of these transitional inverters. So we are doing some empirical tests on this kind of transitional technologies. And on top of that, we can also think about adding additional functions to OLTC SBR so that they can collaborate with DER for effective voltage management. So another technology is called flexible interconnector. And this is called first interconnection and second control. And as for the existing method, there is the fixed interconnection method. And when this is appropriate, when DER hosting capacity is low. But if there is higher DER hosting capacity, this means in order to connect DER, this will require reinforcement or additional capacity with additional investment. So we call this flexible interconnection technology. And with this technology, we'll be able to accommodate more DER. So we can be interconnected first and then decide how to control this later. For flexible interconnection, I won't be able to talk about everything about this, but MTR, capacity, we can look at it from the operational capacities perspective. And as for distributed line hosting capacity, we will increase this to 40 megawatt of installed capacity. And for DR with accumulated capacity exceeding 12 megawatt, they will be conditionally connected with P curtailment. And they can be converted to output during peak time. In order to enable such technology and output control, we need to predict the power output on the previous day. And then we also need to decide how we are going to dispatch this power. And transmission substation and distribution substation, RRMS, ADMS, these are higher level operational platform, and they need to exchange data for collaboration. And this is how these technologies will be applied in Korea. And then I will talk about grid stability. And I've said fault right through. Fault right through will not cover everything about grid stability. But for FRT, this is a function that we need for grid stability. And there was a relevant case in Texas. And as Officer Pang Min-sun has said, she has briefly talked about this case. This happened in the UK, the major blackout. 400 volt TL ground fault has been caused by lightning strike, and this has created instantaneous voltage drop of 8 ms, and plants shut down and frequency dropped further. And many of you might already know that when there is a grid fault, that can lead to voltage drop and frequency drop. And this can create a serial dropout of power plants, creating stability problems for the grid. So the inverters should have this kind of FRT functions because these problems are bound to happen in the future. So we need to be prepared. And when there is inverter connection, will it impact grid stability? There was a question and there was an answer. Renewable energy coming through inverters to the grid. Of course, there will be inertia issues. And of course, clearly it affects grid stability. But in spite of that, if we can control DER and have a good facility, then I believe even if there is an inverter-based problem, we'll be able to resolve that problem and prevent it from having impact on grid stability. So I believe today I won't be able to touch everything because of the limited time, but we need to have this kind of system down the road through flexible interconnection. We need to increase the hosting capacity, and we need to manage the interconnection points effectively. And DER will increase, meaning that distribution of power will also have to achieve the balance of supply and demand. So regarding grid stability, there should be consideration and higher level operation platform like RMS, ADMS. There should be organic collaboration with this high-level platform to achieve grid stability so that we can host more DER and achieve safety of the operation. This has to be achieved at the national level, and there should be national level management system. Thank you very much. That's all I have to say for today. Thank you very much for your attention.
네, 영광.
Thank you very much, Mr. Cho. KEPCO is definitely doing a lot of research for grid stability. And let us move to the last program of this seminar discussion. But before we begin the discussion, we would have to make some arrangements on the stage. So as soon as we are done, we'll start discussion.
네. 그럼 패널 토
Now we are going to start the panel discussion, and I would like to introduce you to the moderator for the discussion, Professor Chun Young-hwan from Hongik University.
통 및 전력
In the area of the system and also in other area, he is an expert. Please welcome Professor Chun Young-hwan. Thank you very much for hosting today's seminar. My special gratitude goes to Danish Embassy and also Danish Energy Agency. I'm sure that all of you have enjoyed tremendously the presentation given by today. We don't have much time, so let me speed up. We have invited 4 panelists, and because we don't have much time, it was really hard to invite these experts, but I'm forcing them to speak briefly. So first of all, I'd like to apologize for that. Let me invite Mr. Kwak Eun-sup from KEPCO. Hello, everyone. I'm from KEPCO.
Now, Mr. Song Tae-young from System Engineering Team of KPX. Hello, I'm Song Tae-young from KPX. Nice to meet you. Now, Energy Transition Forum, Mr. Seok Kwang-hoon from Energy Transition Forum. Last but not least, Mr. Lee Sang-bok from E2 News.
So who should we start first? Well, I believe I have introduced you already, right? So let's begin with Mr. Kwak Eun-sup from KEPCO.
So, since we do not have enough time, well, I just want to say that this Energy Transition Forum I thought it was a forum for policy research, but it seems like it has very in-depth knowledge for inverter technology, and Danish Embassy, Energinet, Danish Energy Agency have come really forward to deal with this issue. And it's kind of amazing, come to think of it. And we have a lot to learn. And Korea is tackling similar issues now. Our situation, I believe, is quite different from that of Denmark because we are an island when it comes to grid. But at the same time, a lot of power generation system is concentrated in one area, and PV power generation is located and concentrated in another area, but demand is concentrated in the Seoul metropolitan area. So grid conditions are very difficult and far worse than that of Denmark. And IVS, inverter-based resource. There's the PV power generation, wind, HVDC, STATCOM, TCSC, everything. And IBR resources will be increased in grid. It seems like an inevitable trend. And as IBR increases, Mr. Kwon from Energinet has talked about various issues like interaction issues, coordination issues, oscillation issues. As capacitance increases, oscillation is bound to occur. And in Korea, the power generation area is totally different from that of demand area. And we have small signal stability issues and frequency stability issues. So we have so many issues in Korea. We cannot avoid IBR as well. All these issues are creating other issues. If these issues are inevitable, then we need to tackle them head on. But the impression I got here is that going forward, I'm sure we'll be able to overcome a lot of issues that we have now because we are doing a lot of research on this. And Korea is very unique in terms of geographical conditions. But when the PV power increases, it could create new challenges. So Korea's set of challenges are quite unique. With expansion of IBR, I believe PV, HVC, they are mainly control issues. But I don't think we can try to resolve everything through controller. That would be too audacious. So we need to coordinate, and between IBR facility and traditional inertia facility, whether it's generator or synchronizer, coordination is needed. And Korea is doing a lot of research in this area. And we really need to refer to what the speaker from Energinet has said. And that's all I have to say now. Well, we were kind of pressuring you to wrap up soon. But Mr. Song?
Well, thank you very much for giving me a chance to speak as a panelist. Looking at the case of Denmark, it's a very small scale system, but I could see that they are preparing for the future. So I learned a lot from Danish example, especially Danish case has a huge implication to Korea. I work for KPX. I'm in charge of system engineering of the power system operation. And I began to think about what do we really need to prepare for the future. So let me speak from that perspective. Many people talk about the fact that we need to learn from advanced countries, especially Jeju Island case is quite risky. So we need to learn so that in case of the inland system, we should make sure that no problem happens. But I can assure you that there could be some risk when we operate inland areas. We need to understand what are the challenges faced by other countries as we expand the utilizations of renewable energy. How and what should we prepare for the future? So let me touch upon the current challenges that we are faced with. Inverter. We didn't have enough functions for the already installed inverter. The PV total capacity about 23 gigawatts, and the function is not well proven until now. Of course, we have revised our grid code. It seems like that it will improve in the future. Second point I want to make is about output control. Capacity needs to be secured for the renewable energy. And when output control is necessary, not only the operator, but also other relevant people need to do that, especially the main electricity is provided by Jeju Island and Jeonnam province, and they need to be able to control the power output. So the possibility of such grid system operation must be guaranteed. Another point is about the vibrations of the inverter. So we need to prepare for that. And oscillation, we need to prepare for that. And next, in the future, what do we need for the system operation in the future? First, transmissions need to be upgraded between the region. In case of Jeonnam province, compared to the necessary load, there are too much PV. So we need to make sure that Jeonnam and Honam or other area can share so that appropriate transmission facility must be well planned out in advance. And also, when there is a power outage or blackout, we need to prepare for that. STECOM and SVC facility must be located at the right place, right amount must be secured so that the grid stability can be guaranteed. Last but not least, this is about the frequency and voltage stability. As the grid inertia is very low, it's likely to be further lowered. Fast DR or pumping or ESS needs to be newly established. We need to improve the existing systems. Inverter facility can provide a virtual inertia. We need to make sure we can use that. This is not something far away, but right now we need it, and very soon we need to make sure that it can be operated. That's all. Thank you.
Thank you, Mr. Song. So you have shared your experience of managing grid from KPX perspective. Now, Dr. Seok Kwang-un. Can I take my mask off? I'm not an engineer, but I have studied HVDC issues for 3 years now. Well, I had an opportunity to look into this issue several years ago, but I could only understand 50% of what the speakers have said today. But I would like to share my experience from the policy perspective. First, the situation in Europe and Korea are quite different, physically different. Situation is in Denmark has AC synchronized with other neighboring countries, and because they had this AC connection, when there were several crises, they were able to overcome that crisis. So it's quite different from Korea, South Korea. We are basically an island when it comes to power grid. But when the renewable energy increases, we are seeing more HVDC on the line as well. And will we be able to overcome the future crisis as Denmark did? Our challenges could be much more severe and challenging than those Denmark faced. And in order to connect with large continental countries like Russia and China, we should also consider switching our national frequency. From 110 Hertz to 220 Hertz, when we switch that, it has it's volt. 220 voltage. Switching that was a major challenge in Korea, but we've gone through that. Has any other country switched their frequency at the national level? I'm not aware of that. So the physical challenges that we face are quite daunting. Therefore, one more thing that I would like to add here is that we have very serious physical limitations, and we need highly sophisticated technologies to resolve that, but our market should be sophisticated first, because we cannot introduce a sophisticated technology in an unsophisticated market. But in the Korean power market, the problem here is that we still have this outdated paradigm of market operation. It's 30 years old, and the civic society tend to look at this based on ideologies. They think power market is the extension of welfare services, and the technological challenges that we face requires sophisticated technology. This requires sophisticated and transparent and highly sophisticated market. But the current status of our power market is trapped in the past, and I'm very concerned about that. For us to have sophisticated technologies adopted in Korea, we need highly sophisticated and transparent power markets. So we need to move beyond ideological debate and look for the best way to restructure our power market so that we can introduce sophisticated technologies and services and also strengthen our system. Thank you very much.
Well, it was already mentioned about SCR being stopped, and also the voltage stability is not guaranteed, and inverter stability is important. But in case of Denmark, I don't think you have an issue with the voltage, right? And in case of Korea, we have diverse issues starting from the voltage to the SDR and numerous other challenges. And I'm sure that you all agree. We need to work harder. We need to do more. That's the situation that we are faced with. And some even mentioned that we need to change the frequency so that we can link with other countries through inverter. Last but not least, let me invite reporter Hvdc Borg of E2 News. Hello everyone, I'm a reporter. Now, Ministry of Trade, Industry and Energy has expanded its divisions, industry market, distributed energy, and power grid management division, etc. But we are handling very, very important issues. But government officials from the Ministry of Trade and Industry and Energy did not take part in. Can you believe that? I am so shocked. I don't know how busy government official is compared to me, reporter. Reporter is much more extremely busier than the government official, isn't it? But I'm here, but they are not. It's unbelievable. Anyway, we don't have much time, but let me speak up. As we expand renewable energy, what kind of influence will there be to the power system? We need to prepare, we need to predict, we need to come up with the plans and alternatives so that nothing can happen. When we talk about that, the feedback that I got is other countries are doing fine. Why? What the hassle? Why are you so complaining about it? That's the response that I got. But I guess that kind of approach is not helpful. We should get rid of such attitude. I'll give another example. We talk about RE100, right? Which is important. And then we even say that renewable energy is easy to do so. That's general feeling, but that's not true. Compared to other countries, Denmark, all the overall conditions are much better from my perspective than that of Korea, but they also had some challenges. And we need to make sure that RE100 and renewable energy, everything easy, that kind of concept should not be firmly rooted. And in case of renewable energy, there is not a single country who solely get electricity 100% from the renewable energy. There are a lot of tons of challenges to be resolved in terms of the technology in using the renewable energy. So from Korea's case, renewable energy using 100% era will arrive soon. That's not possible. It's a road, a journey that is really hard to go. It's an untrodden path, very challenging. We have to overcome a lot of difficulty. We need to admit that. We need to prepare for that. We don't have much time left. So we need to make sure to prepare it in a very wise way. I guess that's helpful for the energy transitions of Korea. That's my main message. Whenever we are faced with a difficulty, with hardship, yes, we suffer, but if we close our eyes or we turn our eyes away or we act as if we are blind, then we'll never grasp opportunity. There's a saying that those who courageously face with a challenge can become the winner. Renewable energy utilization is a goal that we must go and achieve, but this is not an easy thing to do that, and it's extremely difficult. A lot of hardship and bottlenecks and barriers that we need to overcome. We can try everything and anything. Only when we do that, we can at least achieve 2030 goal. And do not dare to say that it's an easy target you can do. Don't say that, because that's like avoiding any kind of upcoming suffering and losing the opportunity to achieve further growth. So let's change our attitude first. That's my favor to ask all of you. And we are faced with these tremendous, horrendous, difficult tasks. I'm a reporter, so I just want to find out the bad things. Wind and PV, if we depend on inverter expansion, if that's a course that we must take, then embedded like additional inland wind power farm could be established, but without having a solid power grid, that's not desirable. So we need to come up with the infrastructure first. I mean, we're talking about nuclear power expansions. I mean, without even thinking about how we can make sure to use the variable renewable energy, why are we going ahead of the actual reality? Hvdc is now established and being operated, but everything is not going in the right direction. From my perspective, if we use the same technology, EQ project, these kind of projects the government is trying to plan, what kind of influence it will give to our grid system and to the new transmissions or new facility, what kind of interaction will there be? Government is not pointing out what are the issues. KEPCO and Denmark Energy, we have a similar agency in Korea, just like DEA. What are they doing? KEPCO and DEA, what are they doing? They're not preparing at all. This is my feeling. They are trying to go to a more difficult road. So let me sum up. We are going to untrodden path and no one has dared to take, but we don't have much time. We cannot walk. We have to run. But without any preparation, we are not preparing at all. We are trying to go more difficult road. So our selections, our concentration are going to the wrong way. We are not trying to overcome the difficulty, but we are only thinking about limitations and faced with a greater hardship. And whenever we talk about this, everyone says being very optimistic and saying that everything will be fine, grid and system is fine. They are saying that that's wrong. In Jeju Island, as you're well aware of, renewable energy visions, they are reaching about 20%, but still the issues are so tremendous that they cannot even dare to find the solutions. Nearly 20% renewable energy, and now they are faced with a heck of problems. We need to resolve that first, and then all the problems that happen in Jeju Island will not be repeated in inland. Before we pay too much cost, we need to innovate our policies. We need to make sure to find the solutions. Do not dare to say that a specific technology is the best answer. Don't say that technology is not the answer. The system operator and also transmission operator and distribution operator, everyone should sit together. We need to open our ears with our hearts and then exchange our views. That's all.
Dr. Cho, would you like to make a final remark? Yes, actually, time is almost up. So we've heard from Dr. Kwon and Dr. Cho. we are trying to go down a untraveled road. We need to build on our confidence, but we also should be humble at the same time. And Dr. Song has talked about oscillation issues in the inverters and generators. And Mr. Lee Sang-bok has talked about EP project. Well, it is true that we need to resolve problems on multiple fronts. The more renewable energy we accommodate on the grid, we will have more challenges. So for today, I would like to thank everyone in the audience for your participation. And as we build on more case studies, I'm sure we'll be able to look for further collaboration active opportunities. And I would like to thank the representatives of Danish Embassy, Danish Energy Agency for making today's seminar possible. Thank you very much. So we would like to conclude the seminar on how to establish renewable energy-centered grid system. I would like to thank all the speakers, panelists, and everyone in the audience for staying with us for long until the end. Goodbye, and thank you very much.